Hello.
I have returned.
You have. How are
It
you?
is I, Paul Sutter.
Hi, Dr. Paul. Can everybody hear him okay? Keep talking while I
I'll
adjust all
keep
this.
talking bombastically, enthusiastically, triumphantly. I have forged into the deep wilderness of the ignorant masses, and I have returned unscathed and victorious.
How was your travels?
It was good. It was nice.
Were your travels? I think that'd be the better verb there. Were, adverb.
I was in San Francisco
Mm-hmm.
for half a week. Attending a workshop put on by the Astronomical Society of the Pacific, great organization. And then I came back here to Columbus and I hosted my own workshop.
Oh, yeah?
Yeah, it was all for teachers, for fifth grade teachers. And we devised demo kits for their students so that they could learn about the solar system and space and all that good stuff. And we trained the teachers on the demo kits so that they could go to their classrooms and spread the good news.
That's awesome. So what was in the kit?
Let me see. One demo kit is called Cosmic Cratering, where you fill up a big tub with sand and flour and cocoa powder,
Uh,
and then you drop various sizes and masses of ball bearings into it, and you measure the crater size, and you learn about potential energy and kinetic energy. And another was just very, very simple globes and flashlights and styrofoam balls, learning about the phases of the moon and the seasons on the Earth. And another one, a fun activity we walk them through, is all about the tides, where you get the kids all in a big circle, and then one walks around the outside, kind of like Duck Duck Goose style. But the kids in the circle have to lean back or lean forward, and they get some sense of how the tides work. We had make your own telescopes and various challenges and games associated with that. And there's one more that I can't remember off the top of my head.
Sounds like it was a fun-filled week, though.
It was intense. There was a
Intense.
lot of running around, and I missed Twitch
Yeah, yeah, you
two
did two
weeks in a
weeks.
row.
2 weeks. And everybody was really sad. But let's see. Okay, so everything it was intense. Were you camping? Some
Yes, it was. It was my. I was a teepee. I was a wigwam. I was a teepee. I was a wigwam. I was. I was too tense.
so no, we just started, but just Dr. Paul just joined. If you guys don't know who he
We're
is,
just warming up.
yeah, just tell everybody who you are. Do you have your book handy, by the way?
Of course, I have my book handy. Funny you ask.
I just, I thought maybe there's the off chance you
Wherever I am, I could be in the middle of a crowded mall and be like, "Hey, Paul, you have your book handy?" I'm like, "Right here."
right here. So he has a book out available for pre-order, guys. It's in the link there. Your Place in the Universe. Understanding our big, messy existence. It's messy.
By me, I wrote it.
He authored it. He made that book. He made that
My
book,
baby.
guys.
It's my book baby. Took 9 months to finish.
Yeah, that's it.
Yeah, it was very painful. So I pretty much understand childbirth now.
That's good. So and when will that actually be available? Like when will people actually get that? When does it come out?
November 20th of 2018 is the on sale date. Available on Amazon. You can get it pre-order on Amazon now, but will be delivered to you on the 20th. You can also get it at Barnes & Noble, Books A Million, IndieBound, and also check your local bookseller.
Ooh, you mean like a library type thing?
Libraries are picking it up, and indie bookstores are also picking it up.
Oh, indie bookstores. I don't know if people even go to the library or
They're
indie
a thing.
bookstores.
They're a thing.
Yeah, I don't remember. So everybody in chat has to say when the last time they went to a library is too, because I'm curious
What
about
is
that.
a library?
What's a library? Just in time for Christmas. Hint, hint. Ooh,
the only quote I remember from the entire run of Inspector Gadget cartoons is Inspector Gadget saying to Penny, "Libraries are just full of defective books."
Oh, I see. I see. I only thought libraries existed in school. Darn. I know. I know.
No.
So
So,
did you follow up? Because I know you had the Parker Solar Probe thing. We actually went and watched your Facebook
oh,
Q&A.
no way.
Yeah, we weren't there live because I wasn't able to make it live, but we went and watched it. Were you getting a lot of questions? Because I couldn't see the chat. We couldn't see the chat.
That was intense.
Was it?
So, something like 30,000 people tuned in,
Oh my God.
and it was just. And so my strategy was like, whenever I looked at the chat, there'd be like a question right at the top of the feed. And then look again, and it'd be a brand new question. So I would just answer whatever was in front of my eyes and go on for a few minutes. And then there'd be another question right in front of my eyes, and I'd go on that for a few minutes. So I missed like 95% of the chat.
Yeah, that's usually the case. I think when you get over 1,000, that's when that becomes a little crazy.
It's basically unmanageable.
Yeah, no, you did good. And some of the questions were really, really good. Some of them were basic, and those are sometimes the best questions.
Basic questions. I think I talked about that in the live stream. It's like the basic questions are the best questions because that's where science starts.
Yeah, and also sometimes they can be the most complicated to answer.
Simple does not mean easy.
No. So we watched that, and that was really, really cool. But did you, so you went to go see the Parker Solar Probe launch, didn't you? Or tried?
No.
Okay.
I was supposed to.
What happened?
Launch delays happened.
Right.
And then they happened again, and then it happened again. And then they happened, the launch got set for that weekend, and that was the one weekend where I couldn't attend the launch. And so I was hoping that they would push it back by one more week, and then it would have been gone. But that narrow 3 days was the one time I couldn't go down to Florida. And that's exactly when they launched.
Yikes.
And I would have missed it anyway, because the way my flights were, originally it was scheduled for Saturday the 11th in the morning, and I was going to fly out that night. And they were like T-minus 30 minutes, and they scrubbed the launch and pushed it back a day. And so I would have had to fly out that night anyway.
Yeah, because they stopped it probably, I think they said like the last 5 minutes of the launch window.
Yeah, it was really close to the close of the launch window.
Yeah. And there were so many people that were streaming it. But hey, I don't know if you knew this. So I have some news for you. So Twitch, how right now we're streaming in IRL because space is IRL, and it's kind of a little bit of real life, at least in my brain. But they're opening up a science and technology channel.
Interesting.
And that will be launched, they're hoping, mid-September. However, it could be, maybe there might be a delay on that. So they're aiming. There
might be a launch delay.
There might be, hopefully it's not like James Webb Space Telescope delay.
Oh, which will never fly.
Right. I'm hoping that it doesn't go that way, but that's like kind of big news, because I was sitting here thinking that we were just always going to have to be in IRL, but we don't have to.
There's lots of weirdos in IRL.
Yeah. Yes.
Yeah. Let's just admit it. We got to be honest with ourselves.
There are. I'm sure YouTube has them too, though, right?
Oh, no, YouTube doesn't have any weirdos. Very mature, very high production quality, very thoughtful content on YouTube.
Always. Yeah. I think YouTube's probably void of all of the weird. So, I was considering
they just went over to Twitch, and now it's very cleanly separated. If you want quality, if you want engaging, you go to YouTube. If you just want to wade around in human garbage and misery,
this is it right here.
Here we are.
My channel,
folks.
Yeah.
I'm just kidding. I love you, Twitch.
Yeah. Awesome. No, they are, and that kind of thing is actually really cool. I'm really stoked about that. Because I know Fraser's doing his virtual star parties, and we're hoping we might have something scheduled for the front page for that. Yeah, the virtual star parties. Really excited about that stuff.
Are you going to be a part of that?
I am.
Nice.
We'll actually be, well, for this one, we'll be doing it here on my channel, but for future ones, I want to be able to go over there, because I think he's actually he's been working on his own Twitch stuff too. So
He has. I've seen him. He's been paying attention, taking notes. He's been asking me questions. He's preparing his own takeover.
Yeah, which is really
Prepare
awesome.
to be caned.
Yeah, but you too, though. Yeah, I'm just gonna bring everybody over to the dark side.
You are the pioneer. You are the log cabin fur trapper.
Yikes.
That's out there.
You can't even finish that sentence. You're done after that sentence. The fur trapper.
Good night, everybody. Thanks so much for watching.
It's been
I'm
really
Dr. Paul
good.
Sutter. My book is Your Place in the Universe, featuring horrible jokes exactly like that one, where I don't even finish the sentence. It just ... and it goes on to the next chapter.
Every chapter is never closed.
No, there's no closure in this book.
Oh man, I needed to laugh. Yeah, so we're gonna do the star party. That's gonna be cool. But I mean, since we have this channel, I think it'd be good for a lot of us that are, the weekly space hangout crew. Even though I've only been on there once, and Dr. Paul also is on that weekly space hangout all the time.
I am a co-host of WSH.
Mm-hmm. So if you guys don't know about that, it's great. And I think we have to have a command for the weekly space hangout. I think we do. WSH. Yeah, see right there. And then, boom, handled. And then also you have your own radio show, Ask a Spaceman. So everybody can find you.
Ask a Spaceman, Space Radio, the book, the articles, the blog.
Mm-hmm. Yeah. So my question is, and we were talking about this the last few times, and again, we're going to have to take your stance again on Dyson swarms. I'm just going to have to ask you first, what do you think about Dyson swarms?
Slightly more plausible than Dyson spheres, but Dyson spheres are infinitely implausible, so basically anything is going to beat that. And every time this comes up, it reminds me that I need to sit down and actually run through the math of how much energy it would take to take all the stuff in a solar system, where most of the stuff is in the planets, or most of the sun is in the star itself, and then take the planetary mass and blow up the planets into tiny little bits to make your swarm, find the precious metals and resources in order to make solar panels and engines and cooling towers and all the other stuff that you need to actually extract energy from the sun, or carbon to grow trees and shrubbery on the inside surfaces of your Dyson swarm pieces, position them correctly, engineer them. That the construction of that takes a lot of energy.
Yeah.
And so you have to take the only way to do it, I'm guessing, the only way to build a Dyson swarm is to take like 1 million years to build it.
1 million.
Because you need to sap a little bit of energy to build your first piece, then you store up some energy for a while, build your second piece, and then your third piece, and on and on. And it probably takes like 1 million years until you've exhausted the supply of material in your solar system, got it in the right orbit, have everything you need to capture the energy, and then maybe you'll see a net return on all that energy after another 10 million years.
Will it be worth it? Mr. Reiber asks. And then Denizen, we got time.
We got time. I don't know. I could see it as a cool art installation because art isn't really worth it in terms of energy expenditure. We just enjoy it, and that makes it worth it. So maybe we'll build Dyson sculptures because we're super bored.
Oh my God, Dyson sculptures? Do you think we could start
Dyson sculptures?
I feel like we should do that. That should be a Burning Man thing.
Yes.
Yeah, I feel like that is total Burning Man art.
Burning Star. At the Burning Star Festival in the Pisces arm of the Milky Way. Only happens once every 100,000 years. And then at the end of it, we let the star go nova and blow everything up.
Yeah, and so Philip says it might cost more than $9.99 as well.
I mean, $9.99. Maybe by then the dollar, there's inflation.
Right.
which would work in the opposite way. Maybe there's deflation, where that's like a million years worth of gross domestic product.
Yeah. Well, someone
So
says
it's like, yeah, given an infinity of resources and time, any intelligent species is capable of basically doing whatever they want, but that doesn't make it a good idea, and no one is required to build a Dyson swarm. It's not the one logical conclusion of civilizational development to end up with Dyson swarms or spheres.
yeah, someone actually just said, wait, what was it? What if it was just a ring around the sun? Would that be more realistic? Would that be a Dyson ring?
Yeah, a Dyson ring. And actually, when I think Dyson swarm, I think Dyson ring, because you can take all the stuff in the solar system, all the stuff, all the planets, all the asteroids, all the comets, and you can put them at, say, the orbit of Venus. I don't know, pick one, and put it in a ring, and you still would cover up barely a fraction, a tiny, tiny fraction of the surface of space at that orbit. You're capturing only a tiny fraction of the star's output, even at an orbit of Venus, even with all the stuff.
Yeah. Isn't Dyson a vacuum cleaner? That's what I thought.
Yeah, they're going big. They've got plans. Right now it's vacuum cleaners.
But
a million years from now, it's solar output energy capture. I've seen their investor briefs. They've got some long-term plans. Puts shame on Elon Musk.
Yeah, and their vacuums probably will get better too, along with that. I imagine their
they'll
vacuums
just keep on sucking.
Heyo. Got him. So let's see.
Yeah, and that's their strategy too, because they have to. Good point, Currens. They need to vacuum up all the stuff in the solar system to get in the right spot. So they're perfecting that sucking technology.
Wow, alien Illuminati. That's all making sense now. So
it's all connected.
It is. So Kronos says, so from the context I get, what a Dyson swarm is basically what. Wait, what actually is it? Kronos doesn't know what it, and it's okay because, honestly, I didn't know this either. I'm not too big on going to any kind of YouTube channels that are talking about Dyson swarms because that's a slippery slope right there. So what is a Dyson swarm?
Just one of the many pieces of garbage on YouTube. A Dyson swarm is a bunch of rocks orbiting a star with solar panels attached to them. ... profit.
Okay. Oh, Kronos says, I understand it, but I wasn't specific. Measurements. Oh, I don't even know. Let's see. I'm looking okay. So Bill Nash says, if we had the ability to transmit that power, lasers, microwaves, whatever, wouldn't it be more practical to position something above the sun orbital plane so that it could be beamed anywhere in the solar system without the sun sometimes blocking it?
Yeah, so this gets into some of the niggling minor technical issues with the Dyson swarm of, okay, you have a bunch of rocks in orbit around the sun, you've got their solar panels, they're charging up their batteries. Now what? You want that energy to do useful things, you want to do work with them, you want to run computers, you want your microwave ovens. So you have to transport that energy, and you have to get it out to distant parts of the solar system, or maybe we're all going to live on the rocks, right? The solar panels. And so I'm in rock number 475, and I'll be having a Twitch conversation to you over in rock 10,017. I guess. I don't know. And then we just kind of live and hang out, and then that's it.
Jezza says it'd be a hell of a power cable.
Yeah, very, very long cables. Gotta pack the extension cords.
Yes.
The Dyson extension cords.
Yeah, exactly. Bring the sun to Pluto, the greatest planet known to mankind.
We could bring Pluto to the sun.
Yeah, we could do that.
Because if you have the energy, if
Right.
you have the energy to build the Dyson swarm, you are resculpting a solar system. So you can basically do anything you want. If here's an interesting statement.
Okay.
If you have the energy needed to build a Dyson swarm,
Mm-hmm.
you don't need a Dyson swarm.
I'm gonna let that just sink in for everybody here because I could see
I have
that.
no idea if it's true, but it sounds awesome.
It sounds so amazing. Sounds great. If you can do it, you don't need to do it.
Yeah, you
Yeah.
already have that source of extreme energy.
Right. I mean, why wouldn't we just go somewhere else?
Yeah.
So and then that brings up the whole thing, like, because I was talking about this with Fraser, the Starshot thing. What?
Yeah.
Yeah. Well, what do you what do you think about Starshot, Project Starshot?
I don't hide my feelings.
No, and it's funny because I asked Dr. Pamela about it too. Just what do you think about that? And first describe what it is. You could tell people what Starshot is.
Okay. Starshot is this horrible idea. I mean, I should be fair. This ridiculously dumb idea that I don't know. I'll be 100% honest. It's
Yes.
we want to send, let's say you want to send something, anything to our nearest neighbor star,
Yeah.
Proxima Centauri.
Yeah.
Proxima Centauri is ridiculously far away.
Mm-hmm.
And it's not just far away in like some vague sense, it is absolutely far away.
4.2 light years.
4.2 light years, which I think puts a mask on it because you're like, oh, just 4?
Yeah, but that's
Just 4?
That's substantial.
That's nothing. I could do 4 in an afternoon.
Yeah.
But the distances are actually insanely long. The time scales, if you're to take our Voyager spacecraft, which are now outside of the bubble of the solar system, if they were pointed in the direction of Alpha Centauri, it would take them, 20,000 years to reach it?
Mm-hmm.
So the question is it even possible to build something, some artifact, a probe, that could reach our nearest star in a human lifetime?
Mm-hmm.
So less than 80 years. And then if it's possible, is it plausible? Is it feasible? Can we actually engineer something like that and afford to do it? Because if you give humanity 1,000 years or whatever, yeah, if you're willing to wait long enough, we could figure out how to send a probe to Alpha Centauri. But can we do it, say, before the year 2100? And the answer that Starshot came up with is, let's take a super tiny thing, because if it's big, like a Voyager probe, if it's the size of a bus or a piano, that's just way too big. It's just too hard, too much energy needed. So let's send something like the size of a postage stamp, like this big. And we need to get it going really fast, like really, really, really fast, like a tenth the speed of light. At a tenth the speed of light, that's a 40-year journey. That is less than a human lifetime. Okay. Well, what goes that fast? Nothing. Rockets can't make it go that fast. Ion drives can't make it go that fast. The only thing that could accelerate that tiny little spacecraft is a laser, where if it has a big deployable sail that's very, very reflective, then you shoot a laser at it, and the light bounces off that sail and nudges it. And that's super slow. That only picks up a little bit of momentum, but it's relentless. And if you shoot this laser at it for, I don't know, a decade, nonstop, eventually that probe will pick up enough speed and it'll be cruising at a tenth the speed of light. And then it flitters out on its way to Alpha Centauri. Okay. Engineering challenges. Well, we'll need the world's most powerful laser, and in fact, a laser so powerful it's even more powerful than the lasers we can possibly even conceive of. It needs to be engineered to such incredibly fine tolerances that produces a coherent beam of light halfway across the solar system, so you can still manage to accelerate this probe. The probe, the sail, the reflective material, needs to be made of some substance that is incredibly, incredibly reflective, because if it absorbs even a tiny fraction of the heat of that laser, you're just going to melt the thing. The probe itself, if we want it to be more than just like a little smiley face doodle on a piece of paper and actually have instrumentation that sends back a radio signal or does some sort of measurement, needs to be incredibly precise. This is the longest term mission we've ever envisioned, needs to be able to communicate with Earth, and in that little postage stamp footprint. And I'm sure I'm missing a bunch of others.
Yes, I think your mic's doing some weird chirping things.
Uh-oh.
Yeah, it's doing this like high-pitched chirp, which, you know, honestly, I've been dealing with.
No, that's me. That's just, I get excited.
Someone said, was that a dog?
Yes. That's the dog we are sending to Alpha Centauri.
Mm-hmm. That's it,
in
responding
the fine
back.
tradition of space exploration.
Mm-hmm. So let's see. And Bill, ask your question. What's your question? You have a question on this topic. And then someone said something, let's see. Getting any percentage of light speed would take some doing. Trying to break them from speeds, that's the problem.
Oh, this spacecraft, if we send it to Alpha Centauri, is not going to slow down. It is going to cruise right through the Alpha Centauri system.
Just like that mic chirp.
To spend like a day there. Just a yep. It'll send back a message. Made it.
Boiled down. Okay, so Bill Nash says, can you talk about the differences in achievable speeds and transit times when you don't have a propellant mass to account for? Can thrust constantly. How does this change how we plan and navigate?
Yeah, so most rockets, almost all rockets, or methods of space travel, when you're in space, you can't push against anything. You can't like reach out and press against the planet and then push yourself off that planet. You need to carry your own energy source with you, and you need to carry your own propellant with you. You need to take something with you that you can squeeze out of one end, and that stuff goes that way, and then your spacecraft goes the other way. And this introduces a huge, huge challenge in rocketry and space travel, because if I want to send something to space and I want it to be heavier, well, then it needs more fuel to launch that thing. But more fuel means more weight. More weight means more fuel, means more weight, means more fuel, means more weight, means more fuel. And this is called the tyranny of the rocket equation, where there's only a certain limit. If you have a certain payload, there's only a certain amount of fuel you can pack on board that thing if you want to zip around space. So right now, when it comes to interplanetary spacecraft, especially deep missions that go to the inner solar system like the Parker probe, or the outer solar system like Juno or New Horizons, we launch them from space, or launch them from Earth. They have a set velocity and a direction, and then we use gravitational slingshots around planets to get extra boosts of speed. If you're talking about interstellar, you can't do that, because there's nothing between us and Alpha Centauri. So your only option, and if you try to look at the numbers of, let's send something like Voyager to Alpha Centauri, you're just never going to win. You're either going to have to, or I'm not even going to say that, you're just never going to win. It will take you minimum 10,000 years to put Voyager on Alpha Centauri. And there is no way around that. So this is why the Starshot Initiative is taking this kind of backdoor approach, where the probe is just the probe, doesn't have any way of adjusting its trajectory, doesn't carry any extra fuel with it. It's just, we're just going to shoot a laser at
it. Squeak Addict says, have we ever observed anything of significant mass actually moving at these speeds?
Oh, that is a good question. So we do see particles traveling close to the speed of light all the time coming from space. We call them cosmic rays.
Mm-hmm.
The fastest macroscopic objects, things that are nice and big, actually, I don't think that Oumuamua is the record holder, but that got a peak speed of 1 or 200,000 miles per hour, if I remember right. So
Mm-hmm.
pretty dang fast, but not even cracking 0.1% of the speed of light.
Yeah, and I think the Parker Solar Probe is supposed to be traveling about what 430,000
500,000.
miles per hour. So that's
That's
significant, but
booking.
yeah, that's
That's
going
booking.
fast.
Oh yeah. Bill Nash. Good point. Good point.
Yeah,
I totally
yeah,
forgot
I
about
was gonna
that.
say, I was gonna say the stars that are orbiting our supermassive black hole, SO2 or S2, whichever way you want to
Yeah,
call
that's
it.
right. That's right. Those stars
Hmm.
orbiting very, very close to black holes that we've directly observed, they're going a certain fraction of the speed of light. Yeah. So yeah, if we had a supermassive black hole nearby,
Yeah, that'd be great because I think yeah,
sweet.
S2 goes around the Sagittarius A star, which is the supermassive black hole. I think every
Mhm.
like 16 or 17 years for one orbit, which is pretty insane. Um, and some of the are some of the galaxies traveling faster than light? Well, that's the expansion of space, right, Dr. Paul? The expansion of space itself.
The expansion of space itself, I missed the last part of the question.
So, well, it's is some of the galaxies traveling faster than light?
Okay.
Okay.
Yeah, take a breath,
Mm-hmm.
everyone,
Mm-hmm.
because this is about to get deep.
Yeah. Real deep.
Our universe is expanding. On average, every galaxy is getting further away from every other galaxy. You can have little local collisions like us colliding with Andromeda, but on average, everything's expanding. The further away you go in distance, the faster the galaxies appear to recede away from us. And at a certain distance, 13 billion light years, any galaxy farther than that appears to be receding away from us faster than the speed of light. Now, you might feel a little bit quizzical about that because I thought we had established that this whole speed of light limitation thing seems to be a cornerstone of physics. So there are two responses about why this isn't a problem with the speed of light. One response, and both of these responses are equally valid, it just depends on which branch of the mathematics you decide to take. One response is that special relativity, Einstein's theory of special relativity, is a local law of physics. It
Mm-hmm.
tells you about what's happening right around you. And it's true, you will never see a rocket blast by you faster than the speed of light. But something way outside, way on the distant edge of the universe, way out there, special relativity simply doesn't apply. You need something broader, more applicable, more general, if you will, something like general relativity. And general relativity says that stuff far away have whatever speed they want.
Mm-hmm.
Another approach, another answer, if you don't like that answer, that's fine. Another answer is that the word speed, this concept of speed, is something you can only measure locally. Speed only makes sense for nearby stuff that's far away. You can measure things like a redshift and an apparent velocity going away from us, but that's not the speed that enters into the mathematics of special relativity that says a speed cannot exceed the speed of light.
And so, question on that though. So, and since I put my chat through hell talking about this last Monday, I believe. Um, so with the speed of light, why can't we travel faster than the speed of light?
We can't travel faster than the speed of light because, and this is the weirdest thing, energy equals mass times the speed of light squared. You
Mm-hmm.
know that E equals mc squared?
Yeah.
Good old stuff.
Mm-hmm.
So I like to take the C out of that. That's just conversion factor. That's just a number. The core of that equation, the most important concept in that is that energy is mass, and mass is energy.
Right.
So all forms of energy have a mass associated with it. A hot cup of coffee weighs more than a cold cup of coffee.
Why?
But because it has more energy. There is more heat. There's more thermal energy in the hot cup of coffee, and energy is mass. If I had a very, very precise scale, super precise, I put a hot cup of coffee over here and a cold cup of coffee over here, the hot cup of coffee will weigh slightly more than the cold cup of coffee. Energy is mass. Me running is more massive than me standing still, because me running, I have some kinetic energy, and energy is mass.
Mm-hmm.
So if I start going faster, if I start going towards the speed of light,
Mm-hmm.
I am increasing my energy. I am increasing my kinetic energy. And that energy is mass. I am increasing my mass. So every time I fire my rocket booster to give me another boost of speed, I put on the afterburners. I now have to push even more mass. And then the closer I get, the more mass, the more mass, the more mass. And I get diminishing returns every time. And if you try to race up to the speed of light, your energy goes up and 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 up. Your energy actually goes to infinity, and your mass goes to infinity as well. And then you're blasting your rockets trying to push something that weighs infinity pounds, and you're never going to crack the speed of light.
Right. Okay. See, and that's a way better explanation. I sat there for like an hour being like, this is why, here's a video, and everybody's like, what are you doing to us?
It's a tough thing. It's a super, super tough. It's one of these things that I found it's really easy to say, like, oh yeah, because if you try to go faster, your mass goes to infinity and can't push something in.
Right.
There's actually a lot going on to uncover in that statement. It's because of that energy and mass equivalence.
So Your Moon says, what if one travels light speed in one direction and the thing you look at travels light speed in the other direction?
Yeah, this is one of these wonderful.
Oh, we got to pause. Oh, it's paused. It's paused. Wow, that face. I didn't do it that time, guys.
All of the weird stuff in relativity, everything about I said about energy.
Oh no. You're breaking up. He's not going to hear for a second. He's breaking up.
All reference frames.
Hold on. You're going to have to say that all over again because you're definitely breaking up. Like that whole answer, I got to say I'm more confused with the answer that you never gave. Yeah, that whole thing you just said. Just you need to have your book handy. So when
good old campus internet.
Yes.
Everyone come, if you're looking for an undergrad university, come to the Ohio State University. We have okay Wi-Fi.
Decent. I heard it. No, you didn't hear it. Nobody heard it. We didn't hear the explanation. Now I'm scared. The man is shutting you down. They don't want you to talk about it. Can you repeat it again?
Yeah, I'll do it.
Okay. And you have do you have Twitch chat open? Because what we can do is if you freeze again, we can do F's in chat.
Yeah, just scream at me. I have the chat open.
Okay.
I'm not paying attention to it, but I have it open.
Okay. So the question was, what was it? Where was it?
Where were we?
Let's see.
Why? Oh, like the shooting the light beam stuff.
Yeah. Well, no. It was. Your Moon. Where was it? I can't find it now.
If you're traveling at like close to the speed of light, and something's traveling away from you at close to the speed of light,
okay, yes.
Then how fast does that light go between you? Well, the answer is you will always see the speed of light traveling at the speed of light. If you're in a rocket ship and you blast a laser out in front of you, the laser will go ahead of you at the speed of light. If you're sitting by the wayside over here and you see a rocket blasting by you and it shoots out a laser, you will see the laser come out of its nose at the speed of light. Same if it's going backwards. You will never not see a different speed in the speed of light in vacuum. And I was going to get into why that's true, but let's skip it.
Okay, so let's see. Right here. Would length contraction turn the universe into a pancake if you got incredibly close to light speed?
Yeah, if you get incredibly close to light speed, there's some cool effects. If you're traveling in close to the speed of light, your view of the surrounding universe actually compresses into a cone in front of you. So you actually start to be able to see stuff that was behind you because the light gets shifted around here, and you end up with this nice cone in front of you where your entire view of the universe is compressed. And then the faster and faster you go, the more and more compressed this little cone gets. And there's also some dangers associated with that, because now you're boosting, you're going really fast. If there's any stray bits of light, like, a visible photon, some normal visible light, that's going to get blue shifted to incredibly high energies and blast you with X-rays and gamma rays. So you'll get a tan. Wear the sunblock if you're going to go fast, close to the speed of light.
And then in that cone, would it be a redshift or a blue shift effect?
It would be blue shifted.
Anything special happen when two particles, each traveling at 90% C, impact each other? That's a good question.
Oh, for sure. They blow up.
They blow up.
It's glorious. This is exactly what we do every day in our particle colliders. We take little particles, we spin them around, get them close to the speed of light, and then bam, kablamo.
And that's it. Then they're like, cool.
Yeah, it's just a fireworks show. It's really just for fun.
Yeah, I mean, I would like that job.
To hit the button.
Yeah. Hit the button.
Now there's two buttons. There's one button that gets it going. And then one button to make the tracks cross each other.
I'll do the second
which
button.
button? You want the second button?
Yeah,
I'll do the startup button.
Please.
And then you do the blow up button.
Yeah, the blow up button's way better.
Says you.
Says
I
me.
actually like the let's get started button.
So then at the speed of light, would the view of the universe be compressed to a point in front of you? I think that's what he was just saying. So then at the speed of light, it would be...
Yep.
Yeah. How long does it take to get the particle to the speed of light? So we've never had a particle get to the speed of light, close to it, but we've never...
Yeah, we can get something like 0.9995 C, if I remember right.
Yeah.
In the Large Hadron Collider. It happens relatively quickly because these particles are very, very tiny. And if you have really strong magnets and stuff, you can get these accelerated pretty quickly. I believe it takes, so Large Hadron Collider is a circle 17 miles in circumference, and I think it takes a couple loops to get it up to speed. If I remember right, I could be wrong on that.
Aren't most particles tiny?
Yeah, that's kind of their definition.
Particle.
Oh, I guess I said you have these tiny particles. I was reinforcing the
You're being a little
particle.
redundant. Okay.
I'm being redundant for instructional purposes only. Of course I know that you know that particles are tiny, but just in case some 10-year-old is watching this, I wanted to reinforce that concept.
Okay, good. 10-year-olds are fine now. Someone said today I learned that there are 3 types of neutrinos, and apparently they can swap between these types. What makes them different?
Oh yeah, this is crazy. This is one of the things that we've only come to learn in the past couple decades, and we haven't fully quite grasped what's going on and why it's going on. So there are 3 kinds of neutrinos. By the way, if you've never heard of a neutrino, it's this tiny ghost-like particle that hardly ever interacts with matter. There are neutrinos streaming through this room and that room and your room all the time, trillions upon trillions of them, but they hardly interact with matter, so you hardly notice them. And there are 3 types. And these 3 types, 1, 2, 3, match up with the 3 types of electrons. You may be familiar with the electron. It's in an atom, makes electricity happen, good old-fashioned electron. The electron has 2 siblings. There's the electron. There's a particle that has all the same properties of the electron, same charge, same spin, same everything, except heavier mass. We call it the muon. And the muon has a heftier sibling, same charge, same spin, all the other properties, but even heavier still. We call this the tau particle. So there's the electron, the muon, and the tau. All the same properties, just 3 different masses. Mirroring them are the 3 neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Now, here is the funny thing about neutrinos. If I make a gun that shoots, I don't know why I got so violent.
That took a real turn.
There was something in me, but
you've been traveling a lot. It's okay.
There were delays. If I make, what's something that shoots something but isn't violent?
We could say I don't even know.
A fire hose. I'm going to be a firefighter.
Oh, okay.
And there's a fire. And I have a fire hose that spews out electron neutrinos. So here they come, electron neutrinos. If I just shoot normal electrons, good old-fashioned electrons, I'll shoot out electrons, and then at the end, at the house fire, a bunch of electrons will hit the house fire. It's pretty much a normal, everyday experience. But if I shoot out a bunch of electron neutrinos, it's not going to be all electron neutrinos at the end of the string hitting the house. No. It's going to be a mix of all the neutrinos. Neutrinos can change their flavors as they travel, as they propagate. Why? We don't know. What are the masses of these neutrinos? We don't know. How often do they mix? We don't know. This is something that we're actively trying to understand.
What's wrong with the rubber band? Oh yeah, rubber band, maybe.
So if I shoot you with a rubber band gun,
oh god,
and it's electron neutrino rubber band.
It still doesn't sound good. I don't want that. Nope.
It's not. I think it's the way I say shoot.
Yeah, it's just in your delivery.
It comes out a little bit.
It's a little rough. So if you have a lepton accelerator and you pump energy into electrons, do they burn into taus? DPI asks.
So electrons, because they're the lowest mass of their 3 siblings, they are the most stable. They'll hang out forever. But the other 2 siblings, the muon and the tau, because they're heavier mass, they will decay into smaller mass stuff. They will decay into electrons plus other things. So a muon has a lifetime of something like 2.2 microseconds, if I remember right, and the tau is even shorter than that.
Okay, you said electron twice, and every time on the word electron, you had your chirp, and I'm dying right now.
Electron?
Thank God.
Electron.
We're fine.
What is going on?
I don't know.
This is your fault.
No, it's not. It's not my fault.
Because you wanted me to have this thing.
I don't know.
The fancy headset with the thing and this is all you.
I didn't know. I just suggested you get a decent gaming headset.
No, you said, Paul, I will not let you back on unless you get a giant dorky gaming headset.
But it works. It's just that word electron just twice on it. It was just perfect. It sounds like a compression artifact on the audio stream.
Electron.
You're good. Try to say it 2 times in a row though.
Electron.
Okay. That's weird.
Electron.
Great. I bet now everybody's going to be seeing electrons in their dreams, nightmares. I don't know.
That's the best part about this book. well, maybe the worst part is that I guarantee all the people who listen to my podcast or have heard interviews with me, I wrote it in my voice.
Did you?
Like, yeah, I just thought, and then as I thought, I typed.
That's good.
So you will hear my voice as you read this book. I will haunt your dreams and nightmares.
Maybe we could do like a chapter reading sometime.
I want to do that. I totally want to do that.
Yeah.
You want to do it right now? No.
No, don't spoil
I'll say
it
no
yet.
for you.
No, well, we'd be out of time. We only have 10 minutes left. You know, I like to really keep track of that time.
Yeah. There's pictures too.
Oh, there's pictures. What's that of?
This is, you remember from the eclipse last year, there's all these awesome maps of the shadow of the sun and where it'd be totality and where you just get partial and all these tracks. Those maps were invented by Edmund Halley of Halley's Comet.
Uh-huh.
And this is his map predicting a total solar eclipse over England in 1710, I think. And that's his map. That's his drawing.
Oh, cool. That's
and
really
he
cool.
was, I think in his predictions, he was just like 4 minutes off. And this was a major triumph of Newton's gravity. Because no human being had been able to predict eclipses until we had Newton's gravity. And Edmund Halley was the first person to do it.
That's actually really awesome.
See?
Don't listen to Jackknife. Jackknife said that you should get rid of the cheesy gaming headset. No, we made him get it. Okay.
And now you're going to live with it.
I think was there more questions around that?
I'm sure there was.
I'm sure. I'm not sure. Oh, we were talking about like particle accelerators and things like that.
And stuff blowing up and changing flavors.
Yeah, and there was a press release. I don't know if you read it, but it was talking about how protons in neutron stars, they do all the heavy lifting. I don't know if you,
cool.
Yeah, I haven't even gone into that, but we can talk about that next time. Let you actually get back and get settled, because I won't have time to read it today either to fully discuss it.
Yeah, neutron stars there's a tiny fraction of protons still left in a neutron star, and they do a lot of cool stuff.
Yeah, because there's not many. That's from what I understood, correct? Yeah. Someone just said, have you read that Zurban's proposed dipole drive? You did link it. I went to it. I didn't know if he had seen it or not.
I did?
Well, no, Bill linked it.
Bill Nash did. Okay, so these words I understand in isolation, dipole and drive, but I don't know what a dipole drive is. There's the link.
So can you? Okay, yeah. There's the link. Do you see that?
Here we go. Well, that guy's hat is telling me not to trust him.
Yeah, that's not a trustworthy hat.
That is not. He's either gonna drive a train, or he's gonna rob my house at 3 a.m.
I'm probably gonna go with the train.
Okay.
Because he is wearing a suit. But it throws off the suit.
It's not working for me. You know, when it comes to fashion, I'm very open-minded. You'll do whatever you want, but you have to pull it off.
Right.
It could be uncoordinated. It could be messy. It could be high fashion. It doesn't matter. You have to make it work. Right. That is the key for me. And that just doesn't work. He's not rocking it. You can see he's not really confident in that hat.
No. He's got one eye winced a little bit more than the other.
Yeah, that's the sign. He's like, I want to wear my brown hat, but it was a little bit too dirty, so I wore this, and it's just not working for you. Sorry, and so I'm going to have to discount your entire idea.
So it says
that hat.
Just because of the
hat.
hat.
Out.
Well, and also the website is centauridreams.org.
Yeah, it's a place where people can go to make stuff up.
Yeah, so let's see. So it says, one reason we look so often at sales. Let's see. He's presented the work. Read on. I want a TLDR.
This is a long piece.
This is
which is also a bad sign.
Oh,
wait,
wow.
There's lots of comments.
Wait, this is the dipole drive. Okay, wow. Do you hear this scrolling?
Is
Oh
that
my,
that sound of wind?
those are comments. Okay, so about, a little bit under a quarter, you start getting into, the next big future. Can we just not name websites like this? Centauri Dreams and the next big future?
Yeah.
Wait, this is
Yeah.
like EM drive stuff. What do you feel about EM drive stuff?
There's no such thing as an EM drive.
Oh,
There's a bunch of microwave ovens that don't move around, and that's it.
well, there's actually, okay, so this isn't EM drive stuff. Let me correct myself. It says
It's
there's
not
a,
an EM drive. It uses electromagnetism, and there are ways of deploying electric cords, long electric like tethers, and using that to wave around in the Earth's magnetic field to give you some torque and lift up in space. As soon as you get away from the Earth, you're sunk because the sun's magnetic field isn't strong enough.
yeah. And
Yeah.
it's so funny. I knew people would come in probably in things like this. Um, so the basic concept of the dipole drive supposes that protons in an electrical field, and described by author situation and system, will create greater thrust than an electron. Is absolutely false. What?
Protons have more mass
Right.
than an electron,
Mm-hmm.
but yeah, I don't know. Then where are you getting your protons from? This is the basic like rocket thing. Like the more stuff you can send out the back, the more your rocket will get pushed around. But in order to send something out the back, you have to keep it in the cargo hold. So, and you have to get it up into space in the first place. So, if you want really, really stuff like, hey, I know, let's throw bowling balls out the back
Mm-hmm.
instead of styrofoam. Sure, when you shove a bowling ball out the back, that'll push you more than a styrofoam ball will, but the bowling ball is heavier.
Right.
So it makes it harder to get into space. And then when you throw the bowling ball out, you still have this giant pile of bowling balls, which means you're not going to move very much. So there's always that balance. So yes, protons shoved out the back will give you more thrust than electrons, but you need a big giant box of protons, which is going to be heavier than a big giant box of electrons. So it's not necessarily true that you'll have a more efficient propulsion method with a heavier reaction mass.
Oh man, people are getting in some arguments in this comments. These comments, yes.
Bring it.
Yeah, they're getting some technical stuff
I
here.
will chirp at you until your ears bleed.
Yeah, I've never actually heard about this at all. At all. Interesting stuff, though, huh?
Sure.
We'll just use the
You know what
Dyson
else is
Swarm.
interesting?
Oh God.
The whole entire universe. As
Your
revealed
book.
by the lens
Your book.
of scientific exploration.
Have you done any recent videos that I know you just put out one not too long ago, but that we could go to and watch maybe after we're done with your interview?
Yeah, let me see.
Do you have a favorite? Do you have a favorite?
I have a favorite. I did a 4-part series on general relativity.
Oh.
Which was digging in deep. Like it was actually following Einstein's path and line of thinking to get to general relativity. So it's all about his thought experiments and all of the situations he imagined trying to get at these fundamental truths and build a mathematical make mathematical sense out of all these situations. That was a fun series.
And that one would be found on your...
That's on my YouTube's Ask a Spaceman.
Okay. Yeah, because I see you started Cosmic Inflation. Yikes.
I just started a new series all about cosmic inflation.
Yeah, that one's gonna... And so how many parts do you think you're gonna have with that one?
Let's see, because I recorded it all. It's all scheduled. Let's see. I forget if it's a 2-parter or a 4-parter.
With inflation?
with inflation. General relativity was a 4-parter,
Mm-hmm.
and inflation is a 4-parter. The first episode is out now, Problems with the Big Bang. Next is Death to the Monopole Monsters. 3 is Accelerated Expansion. 4 is The Seeds of Structure.
So it's going to be a 4-parter.
That's a 4-parter.
Okay. Yeah, because I think we did talk about GR, but this might be actually good to go through this with them, and then we can watch the other one too.
Yeah, the Road to Relativity 4-parter. It's building the bones of general relativity.
Yeah, I think there was someone actually in my chat that asked, like, it'd be really interesting to like see how he did this, like how he arrived at this, and that's kind of what you're saying.
It took him 7 years. 7 years, start to finish.
That's not that long.
I've never done anything for 7 years.
But marriage?
Oh.
Yeah.
Stayed faithful to my wife.
Got it. There you go. Now you can say you have.
Check. Which Einstein did not manage.
Right, that didn't happen there.
Ha.
So
one up on you, old Al.
So right before we go,
you have general relativity, but do you stay married to the same woman?
Oh. Nope. Heyo. So Necrotic has a question. So Dr. Paul and Skylias, how would I get into physics, particularly the more advanced math involved, if I have a horrific track record with algebra?
Okay. Mm-hmm. Yeah. So the tone I've taken my podcast and my YouTube series is almost from not a top-down approach, but where like I start from the math. I start like how a physicist or an astronomer learns about the topic and understands the topic and deals with the topic, and then I do my best to translate that into natural English language and try to explore all these concepts and the interconnectedness and the relationships that are very fundamental in physics. And it is sometimes it's relatively easy math and sometimes it's ferociously difficult math. Like the equations of general relativity are horribly messy.
Mm-hmm.
Quantum field theory is a snake bit. The thermodynamics and flows, involving magnetism, that gets all complex. It's different branches of mathematics are used in various ways in different kinds of physics. So in a college education, in a grad school education, you start with that algebra and the calculus, and you build off of them. So by the time you're in calculus, you look back at like elementary math, you're just arithmetic, and you say that's for kids. At the end of a grad school education, you look back at calculus and see it as just as a fundamental building block for the stuff you know now. And so at first that sounds incredibly intimidating, but that's only because you haven't been immersed in it for well over half a decade, closer to a solid decade.
Mm-hmm.
And this is why training physicists takes so long, is because it takes a very, very long time to give you the pieces of knowledge to make yourself a competent physicist in the 21st. You start with where you are in your math, and you go one level deeper, and then you master that, and you go one level deeper, and you master that, then one level deeper. But it starts from where you are. It starts with algebra and calculus
mm-hmm.
and geometry.
Yeah, and there's a bunch of things like, you can do like Khan's Academy has a bunch of stuff with like,
yes.
Getting better at and getting more comfortable with it. I think a lot of things when people are learning things in school, that can add a whole different level of stress where your brain's just not.
That's true.
Like learning things like when I was able to sit down and understand math better by myself, it was so much easier. So I do suggest that, but. Well, thank you so much for the time, and I'll hopefully see you next week, maybe?
Yeah, possibly. I'll be traveling again next week, but I hope to be able to Skype in.
Okay, sounds good.
Or Zoom in, or whatever
Zoom.
The heck we do.
Yeah, it's Zoom. All right, this is Dr. Paul, guys. I'm going to have his link up in here, and we're going to watch some of his stuff on how to understand gravity, and he has a book available for pre-order. All right. We'll see you
Yeah,
maybe.
we'll do a chapter reading. That'll be fun.
Yeah, we should. Okay. I'll catch you maybe
right.
next week. Maybe.
Maybe.
Okay.
Take it easy.
Bye.